Good morning, chemistry team. You ready for video number 11 in our buffers and titrations journey? We are literally at the end of our journey for second semester general chemistry. We've done titrations in great detail. No excuses that you haven't seen everything. For strong acids being titrated by strong bases. We did a huge one on weak acids being titrated by strong bases. I did not flip the strong though. I didn't do a strong base being titrated by a strong acid. Same idea, just the mirror image of it. But I am going to do a weak base titrated by a strong acid. That's going to be this probably two-part video. And then we'll briefly talk about polyprotic species being titrated. We're done, baby. Woo! And then on to summer and recording all the videos for first semester of general chemistry. Yay! So we're going to have a battery of everything up here. Good thing about these videos is you can pause, rewind, watch things over again. So you can really learn your stuff with these babies. All right, what are we going to do with a weak base titrated with a strong acid? It's exactly the same concepts and steps. You see the 6-step process behind me there. We had a 6-step process when we titrated a weak acid with a strong base. All right, no different. Calculations are exactly the same. It's just everything's a mirror image of it. It's kind of backwards. So many examples are done with the acid being titrated by a strong base. So when we flip it around and take a base being titrated by an acid, our brains go, because everything's backwards. So let's go through in great detail so you can see how this works out. And I picked one I thought was a little more challenging. It doesn't really matter what the identity of the base is. You can see the thinking process. When you get the steps down, when you get to the exam, step 1, step 2, step 3, you know what to do. Or if I do one particular step on a problem, say I just do a problem and just say, what's the pH at the equivalence point? You go, oh, okay, and that's step 5. Okay, I know what to do here. And you just know how to approach it. So here's the steps for a weak base. Now remember, we're starting with a weak base. So I'm going to give you the concentration and the volume of that weak base. It would be in your Erlenmeyer flask in lab. Add your indicator, swirl it up, maybe add a little DI water to give it some bulk. Have a nice white background so you can see color changes of the indicator, whatever indicator you're using. And then you're going to add your strong acid to it, probably, hydrochloric acid or something. Of course, the very first thing I like to do when I'm looking at calculating a pH titration curve, so the volume of the titrate this time on the x-axis will be the volume of the strong acid, and then of course pH would be the y-axis there. But we're starting with the base this time. With the acids, we're starting at a lower pH, doing that S, hitting the equivalence point and moving over. Now we're going to start at a higher pH. It's a weak base. Not as high, not probably up to the 13 range. That'd be a strong base, but still up pretty high in the pH range. And then we're adding the acid, but we're pre-equivalence. We still have more base than acid. And then all of a sudden we hit the equivalence point. Boo! Down we go off of the cliff. And then we're in the post-equivalence region, and we only have leftover strong acid. So that's going to drop pretty low, down probably below 3. So it's just kind of that reverse mirror image of what we have. Calculations are the same. Don't freak out about it. So let's find the volume of the titrant, the strong acid at the equivalence point, so we know where the pre-equivalence region is and where the post-equivalence region is. It's always a good start. And then steps 2 through 6 you can do in any order you want. It's irrelevant. I'm just doing them in this order because we're moving along the chain. So first I'm going to calculate the initial pH of that weak base. So we're going to set up an equilibrium for that and do a nice table just like we did for the weak acid. Then we'll calculate something in the pre-equivalence region, hopefully butting right up against within a milliliter of the equivalence point right there. And we're going to form a buffer. So we're going to have all the acid will be gone. We'll have some leftover weak base, and we will have formed some of its conjugate acid. So B for weak base, BH plus for the conjugate acid. It picked up the H plus. So we're going to have a mixture of those two. That's a buffer. So we can use the Henderson-Hasselbach Equation. So you would do your neutralization stoichiometry, figure out the concentrations of each of those. After you added the acid, plug them into Henderson-Hasselbach. Boom, you're good. Then we'll do the half equivalence point. Now with an acid, the pH was the pKa of the acid. For a base, the pOH is the pKb of the base. And then you just subtract the pOH from 14, you got your pH. That'll be a quick one. Step 5 again, equivalence point, exactly like we did for the weak acid, but for a weak base, when you're at the equivalence point, the only species present is the conjugate acid, BH+. That's the only thing that'll be left. So that will set up an ice to figure out the concentration of it. We'll set up an ice table for it, and then figure out its Ka and its concentration and all that fun stuff, and calculate X, and we're good to go. And then the post-equivalence region, all the weak base is gone. So all we have left is the strong, well, the dominant species is the strong acid. You'll have the conjugate acid there, but it's weak, so we'll just ignore it. The contribution of H2O plus will be from the strong acid. So you just do neutralization stoichiometry, how much strong acid you got left over. That gives you the H2O plus, take the negative log, and you're good as gold. Let's go do it, yes. Ready for our last major problem, even though it has 6 steps to it. So it's really a 6-for-1 special, yay! And a couple of them, remember the equivalence point's pretty challenging to do. The pre-equivalence, other than the half equivalence point and the equivalence point, are some doozers. But if you know the process, you can do it. All right, here's an example of something you could see, fair game, on quizzes and exams. We're having titration. We have 27.52 milliliters of 1.39 molar. Whoa, we got some weird looking species there. You may never have seen that before. 3 methyls, that looks like trimethylamine. And if you're not sure, if you're like looking at it going, what the crawdaddies is that? I don't know. But you see the nitrogen, you know that's an ammonia. So really that's just ammonia with all the hydrogens replaced with methyl groups. So what you can do if you want to just make yourself feel more comfortable is look on your KB table and you can see it right there. Right? You see the CH3 taken 3 times N. So that's your trimethylamine, and there's your KB value. So that might make you, so I would recommend taking some time and looking over some of these weird ones, especially some of the ones you're familiar with. All the good things come with the means. We're going to titrate that weak base. So that tells us it's a weak base. You should recognize it with the nitrogen there. With 1.50 molar hydrochloric acid solution. So we're recognizing the problem as a weak base. Imagine we put that, the 27.52 mils in an Erlenmeyer flask with an indicator and some DI water for some bulk in lab. And then we fill up our burette with our clear colorless titrant, 1.50 molar HCl. Although in lab, I would hope you'd get more significant digits than that. Right? You probably want that to 4 significant digits in lab. Here we go. Now that we got it, you don't know what I'm going to ask you on the exam. I could ask you any one of the 6 steps, right? But this is kind of a first one. What volume of hydrochloric acid solution is necessary to hit the equivalence point? So let's do our stoichiometry. Let's write our neutralization reaction first, and then we'll do some stoichiometry. Exact same concept. It's just a little trickier because the amines, they give us some weird looking products on the far side. All right, so let's do our equation. So we've got let's write our trimethylamine down. There's worse ones, trust me, if you look on that table. So we got a solution to that. And we'll go ahead and just do the molecular equation. You could do the net ionic. Really, the chloride's not really doing diddly squat. It's just the H plus is going boop to that nitrogen. It's kind of like the ammonia NH3 forming NH4 plus. Same idea. So just ignore what gobbledygook is there. It doesn't really matter. So let's move that over. So we're going to get CH3 taken 3 times. Those carbon-based groups don't do anything. The nitrogen picks up a positive charge, and a lot of times in organic chemistry you see them circle that charge. I've seen that quite a bit. Not critical, but if you want to circle that charge, that's fine. Now the chloride ion, you can do one of 2 things. You can either just write it with it like this. Commonly you'll see that done in organic chemistry, or you could split it out, understanding that's going to split. So as a molecular equation, that's really kind of what we should do. But sometimes you'll see this. You'll see people write it as AQ plus Cl minus. So that's really kind of a mix of a net ionic and a molecular equation. But we're just trying to get to the point we have a 1-to-1 mole ratio here. That's all we really need. So I'll just leave it like that because I don't want to erase it again. And we're focused on, here's the weak base, forming its conjugate acid over here. All right, so what I want you to do on your own is using that equation, knowing that you have a 1-to-1 mole ratio or millimole ratio, take the volume and concentration of the trimethylamine weak base, convert that into the volume of the hydrochloric acid required at the equivalence point. Pause the video and do it. Hopefully you got something that looks exactly like this. All right, you might get the answer, but I'd like to see that your work. I want to see the Ionization Equation, all the units cancel out. So we're starting with the volume of the base solution. Use the concentration as a conversion factor to cancel out solution volume to get to the millimoles of the actual solute. And I got lazy there and wrote base. A lot of those organic ones, you don't want to write that formula. So multiply the concentration times the volume. That'll get you millimoles of the trimethylamine in there. And then, of course, from the equation, we can see that 1 millimole of the base reacts with 1 millimole of the acid. And then I use the concentration of the acid, which is 1.50 millimoles of the solute per milliliter of the solution. And if you want to cancel out your units, you can see the base solution volume goes bye-bye there. Millimoles of base goes bye-bye there. Millimoles of the acid goes bye-bye there. And you're left with millimoles of the acid solution. Yay! We got 4 significant figures, 3 exact 3, so we're good to 3 significant figures. I get 25.501 milliliters of the hydrochloric acid solution. So that's closer to 25.5 than 25.6. So we'll keep it at 25.5 milliliters of acid solution. So that's the middle point of my titration curve. Any volume before 25.501 is pre-equivalence, and anything past 20.5.501 is post-equivalence, and the mathematics are different for each one. So now let's go to step 2. Let's calculate the initial pH of the trimethylamine, the 1.39 molar trimethylamine, without having added any acid yet. See if you can jump on that before I erase my board. Here we go. What is the initial pH, right? Only the weak base. So I always understand what is present. What do I have to worry about? And since that's a weak base, that'll ionize in water, right? So let's write that ionization equation. It takes a while. So I've got my weak base, haven't added any acid yet. So that will form an equilibrium, and it's a base, so it's going to be taking an H+, right? Acids donate. That's the Bronsted-Lowry concept. So we're going to get the OH- and the conjugate acid here. So you pick up, whoops, I forgot a hydrogen there. You pick up the hydrogen and the positive charge. And there you go, right? So the water becomes OH-, that becomes the conjugate acid. Let's set up an ice table. So go ahead and do that for me. Draw your ice table. Sound effects are optional. I don't care how pretty your ice table is. Doesn't matter. We've got our species. There we go. And the water's a liquid. Liquids and solids we don't care about, right? Let's put in our values here. What was our starting concentration for that weak base? What was that? Was that 1.39 or something like that? So we're starting at 1.39 molar there, and we had none of those. So pretty obvious Q is going to be 0. So Q equals 0, which is less than K. So that's going to shift to the right, obviously. So we're going to get negative X's here and positive X's there, just like we've been doing 100 billion times. Billions of times. So we're going to lose X amount of that when that ionizes. It'll drop a little bit. We're going to gain the same amount here because everything has a coefficient of 1. And gain the same amount there. This should be old hat for you guys. So let's take the initial plus the change. So 1.39 minus X. That'll be the equilibrium concentration for the trimethylamine. 0 plus X is X. 0 plus X is X. Broken record. Some of you have never seen a record. All right, here we go. Let's do our KB. So KB will be the products over the reactants. So that's going to be these weird looking species. So we got the trimethylamine concentration raised to the power of 1 times the hydroxide raised to the power of 1 over the well, actually, that's the trimethylammonium ion, not trimethylamine. That darn organic stuff. So let's put our original weak base here. There's your trimethylamine, and then the trimethylammonium ion. That's our setup, all raised to the power of 1. Let's see what we got here. That's going to be X. That's going to be X. So much nicer in terms of X. So let's put X here, X there, and then the trimethylamine is 1.39 minus X. What do you think you're going to do? Unless you really want to do the quadratic equation, which is not allowed on my exams, we're going to assume X is super small, so that 1.39 minus X is 1.39. So let's make this approximation that that's X squared over 1.39. So now if this assumption is valid, X, which is the OH minus concentration, will just be the square root of Kb times 1.39. Identical to what we did in the last problem. We just had a Ka instead of a Kb. And that'll give us OH minus instead of H3O plus. So let's do our assumption. I'll have to do that on the next board here. Let's test this assumption that it creates less than 5% error, and then go ahead and solve for X. I'm going to erase my board and do it. See if you can solve for X before I'm done. Let's walk through the calculations. All right, there's our assumption. Kb is approximately X squared over 1.39. And if you look up the Kb value, which we did earlier, for trimethylamine, 6.3 times 10 to the minus 5, right there. That's from the Kb table. Let's do the assumption. So if you take the molarity of the base divided by Kb, so 1.39 divided by 6.3 times 10 minus 5, if that's bigger than 100, this is a valid assumption. Or you could just solve for X divided by 1.39 times by 100. If that's less than 5%, you're good. So when I do that, I get 2.206 times 10 to the 4th. Go to two significant figures from the Kb. That's way bigger than 100. So pretty safe in saying X is small is valid. So 1.39 minus X is about 1.39. We're good with that. So X, like I said, will be the square root of Kb times 1.39 because you got the X squared term. Got to take the square root of both sides. So plug in your Kb of 6.3 times 10 minus 5, multiply by 1.39, and take the square root of that, and I get 9.357 times 10 to the minus 3rd. That would be molar. I didn't have room for my molar there. I'll squish in a little molar. Squishy molar. Good to two significant digits. And from our ice table, X is the OH minus, the hydroxide ion concentration. So if we take the negative log of the hydroxide ion concentration, that'll give us POH, right? So negative log of 9.357 times 10 minus 3rd, two significant figures. In the log term gives us 2 decimal places. So I get 2.0288. Good to 2 decimal places. That's the POH. Remember, we're plotting pH for our titration curve. So we know that pH and POH added together is 14.00. How many times have you seen that trick there? So let's take 14.00 minus the POH. So 14.00 minus 2.0288. 2 decimal places, 2 decimal places. So I'm good to 2 decimal places. I get 11.9712. Good to 2 decimal places. That's closer to 11.97 than 11.98, so that rounds to 11.97, which makes sense. We're starting with a weak base. We're way up on the pH scale there with a weak base. So for our titration curve, we're going to start up high. It's not a strong, right? It's not 13-ish or something like that, but that's a pretty high one, approximately 12. All right, that's our initial pH. Let's do some pre-equivalence work. Yay! On to number 3. All right, we're going to do 2 data points in the pre-equivalence region. We're going to do one butting up against the equivalence point volume of titrant, and then one at the half equivalence point, just because that one's really easy to do and gives us a nice, easy data point. So let's do the harder one. Somewhere in the pre-equivalence region, and we calculated 25.5-ish milliliters of our HCl titrant to hit the equivalence point. So anything real close to that, maybe within a milliliter. So I just said, let's say, what's the pH after adding 25.00 milliliters of hydrochloric acid solution, which is the titrant from your burette. Let's go ahead and calculate that. If you want to get a jump start, that's fine. But again, let's write the neutralization equation down. Start with the neutralization stoichiometry. All of the base will, all of the acid will run out. We have more base, less acid. Got to think backwards here. So we got to figure out what's the new concentration of the base after it got neutralized partially by the acid. And then we're forming the conjugate base. So we got to figure out what's the concentration of the conjugate base formed. And then we have those two concentrations, plug them into the Henderson-Hasselbach equation because we're going to have a buffer. Let's do it. Now, you probably already have your neutralization equation written out from before. I just had to rewrite it, but you don't necessarily have to. So let's think about what's happening here. We are starting with some base. Oops, that's not H2O. That's going to be HCl. I was morphing my ionization equation in there. So that's going to react with the titrant, and you're going to get the conjugate base, chloride ion. Not worried about the chloride ion. Let's figure out, just like we've done for all the titrations, how many initial millimoles of base we have. We did acid before, but let's see how many millimoles of base we have in that Erlenmeyer flask to start with. And then how many millimoles of acid titrant are we adding to it? Which one's the limiting reactant? Which one runs out first? Obviously, in the pre-equivalence region, the titrant runs out first, and you have leftover of the initial acid. In the post-equivalence region, the original species you are titrating runs out, and you have leftover titrant, regardless if it's acid or base. So in this case, the acid's going to run out, and there'll be base left over. But you can see it from the math if you get confused. Let's take the starting volume of our trimethylamine solution, 27.52 milliliters of solution there. Multiply it by its concentration, 1.39 millimoles of the trimethylamine solute per milliliter solution. Milliliters of solution cancels out. Bye-bye. To 3 significant digits, I get 38.252 millimoles of trimethylamine. That's how much we got starting in that Erlenmeyer flask. Then how much titrant are we adding? Well, let's take the volume stated in the problem, 25.00 milliliters of hydrochloric acid titrant, times its concentration, which is provided in the original problem, 1.50 millimoles of HCl per millimole of HCl solution. Milliliters of solution cancels that. Again, concentration is just a conversion factor between solution volume and solute amount. To 3 sig figs, that gives us 37.500. You don't really need the 2 zeros after it there, but that's how many millimoles of HCl. Can you see that 37.5 is less than 38.252? So the acid is your limiting reactant. That's going to run out. And that will also determine how much of the conjugate base forms. So the number of millimoles of hydrochloric acid that got wiped out will determine the number of millimoles of the conjugate acid that you form. So that 37.500 will be the number of millimoles of the trimethylammonium ion you form. And then you just divide that by the total volume of the acid plus the base, and you got the concentration. That's your BH plus in the, if you look in the Henderson-Hasselbach equation, this would be B, the base, and that would be BH plus the conjugate acid. So we got to figure out the concentration of the original base leftover. So just take the millimoles, you just subtract these, right? And that'll be the millimoles of the base leftover divided by the total volume. So get the concentrations of both of those, plug them into the Henderson-Hasselbach equation. Let's do it! A lot of calculations, but not difficult if you know what you're doing. Sounds like life in general. So here's our intermediate steps. Let's figure out how many millimoles of the original weak base we have left over. So take the starting millimoles of base we just calculated, 38.252 millimoles, minus the millimoles of acid that we added, that's 37.500. Both are good to 1 decimal place, so our answer is good to 1 decimal place because we're subtracting. I get 0.752 millimoles, good to 1 decimal, which leaves us with 1 significant digit. That's how many millimoles of the trimethylamine are left after neutralization, right, in pre-equivalence region. All right, how much of the conjugate base, conjugate acid did we form, the trimethylammonium ion? Well, that will just be equal to the amount of the limiting reactant we had because they're in a 1-to-1 ratio. I'll kind of skip some steps there. So we had 37.500 millimoles of the hydrochloric acid. All of that gets wiped out, so that limits how much of the product we can form. So we'll form 37.500 millimoles of product, which is our trimethylammonium ion, our conjugate acid. And that's from the limiting reactant. You're welcome to show the 1-to-1 mole ratio from the stoichiometry if you want to, or you can just pop that in there with that designation. Hopefully, if it's obvious to you that those are going to be the same, I'm fine with that. And then let's figure out the total volume after we add everything together. So the volume of the base originally was 27.52 milliliters from the first problem. We added 25.00 milliliters of acid solution, both good to 2 decimals. So the total volume is 52.52 milliliters. All right. So just take the millimoles divided by the total volume. That'll give you the concentrations of the weak base and its conjugate acid. Plug it into the Henderson-Hasselbach equation. Let's go for it. Did you get the same concentrations I did? All right, so our weak base, the trimethylamine, which we could say just is B, would be the 0.752 millimoles, good to one significant figure, divided by the total volume, 52.52 milliliters of solution. So to one significant digit, I get 0.0143 molar. That's the remaining base. Let's take the conjugate acid formed, or BH plus, in the Henderson-Hasselbach equation. That'll be the millimoles formed, 37.500 millimoles, good to 3 significant figures, divided by the total volume. Got to watch out for dilution, right? 52.52 milliliters. Good to 3 significant digits, I get 0.71401 molar. Again, good to 3 sig figs. I'm going to put the rest on another board, the Henderson-Hasselbach equation. Just plug in your B and your BH plus. Fine, we know the Kb value. We should be able to get the POH pretty readily. All right, Henderson-Hasselbach equation for weak base conjugate acid buffers is POH is pKb plus the log of the conjugate acid over the base. Mimics the one for weak acid buffers where you had pH is pKa plus log of the conjugate base over the original weak acid. I gave you those equations on exams. Just got to recognize if you have a weak base buffer versus a weak acid buffer. So we'll be able to get POH from that. So plug in the BH plus, the conjugate acid, the trimethylammonium ion. Plug in the B, or the trimethylamine. We got the Kb. We already looked that up. So, and again, if you forgot what the Kb value was, just look it back up on your table. 6.3 times 10 to minus 5. So we're going to take the negative log. Since that's less than 1, the log of that will get a negative number, which cancels out with that negative, giving us a positive 4.2006. 2 significant digits in the log term gives us 2 decimal places. Over here, the concentration of the trimethylammonium ion, the conjugate acid, was 0.71401 molar, good to 3 sig figs. The concentration of the weak base left over, the trimethylamine, was 0.0143 molar, good to 1 significant digit. So when we do that division, we'll get 1 significant figure. The molarity terms cancel out. So 1 significant figure means we get 1 decimal place in our answer. So that's why we have 1 decimal place. So the log of that term would be 1.698, good to 1 decimal place. So if I take 4.2006 and add 1.698, 1 decimal place, 2 decimal places, so I'm limited to 1 decimal place in my answer from the addition, I get 5.898. That is the POH. We got to subtract that from 14, right? pH plus POH is 14. So 14 minus 5.898. We got 2 decimal places there and 1 decimal place there, so we're limited to the tenths place. So I get 8.102, which does not round up, stays at a pH of 8.1. Does that make sense? Well, yeah, we're in the pre-equivalence region. We started with a weak base. We added acid to it, but there's less acid than base, so we have leftover acid, so it should still be a pH greater than 7. It's still basic. There's a little bit of base left over, and we're rapidly approaching the equivalence point. All right, you should easily be able to do the half equivalence point. Let's do that real fast. It takes like 20 seconds. All right, problem number 4. We're still in the pre-equivalence region, just doing this one special point, the half equivalence point, because it's so easy. Might as well. So what's a pH at the half equivalence point? Well, what's the volume? We need the volume so we can do our titration curve later. So the volume at the equivalence point we calculated in step 1 was 25.501 milliliters. Well, half the equivalence point would be half of that, which would be 12.750 milliliters, rounded to 12.8. So we have that data point on our x-axis. What's the pH there? Well, by definition, the weak base concentration equals the conjugate acid concentration. So the trimethylamine concentration should equal the trimethylammonium. You don't have to calculate it. They're going to be the same, and they're going to cancel out in the Henderson-Hasselbach equation. Yeah! So POH is pKp plus log of the ratio. Well, that ratio is 1. The log of 1 is 0. So POH equals pKb. This is the same thing for acids, but for acids it was pH equals pKa. So we already calculated this. So the negative log of 6.3 times 10 minus 5 was 4.2006. That's the POH. Subtract that from 14. Two decimal places, so 14.00 minus 4.2006 gives me 9.7994, good at two decimal places, rounds up to 9.80. That's the pH at the half equivalence point, which makes sense because we have leftover base. Easy to do. You can skip all of this and just say POH equals PKP. By definition, you're good to go. Let's go on to the next. We'll do part 2 videos.